Okay, now I'm going to prove mean value theorem in 3D. And there are two equations you should know. One of them is gradient v equals dv dr in r direction plus 1 over r dv d theta in zeta direction plus 1 over r sine theta dv d phi in phi direction. And you should also know that in spherical coordinate, a little surface dA equals r squared sine theta d theta d phi, where theta is this angle and phi is this angle. Okay, so we start by using Stokes' theorem. So by Stokes' theorem, this is a surface integral of gradient v multiplied by dA in n direction equals 0. So the surface, we assume the surface is a uniform sphere with radius r. So since gradient v has dv dr component in r direction, and direction is r direction, this can be dv dr times dA equals 0. Okay, so dA is r squared sine theta d theta d phi equals 0. Since r, we can choose any value of r. It doesn't matter if it is not 0. So if r is not 0, you can write it in this form. So now we think this equation as an integrand, and we put on another integrand where r goes to epsilon to large r. This equation should also be 0 because integrand is 0. And if we change these dr and d theta, we can write it in so if we choose in this form, this is the same equation as the following equation. So we separate the equation. And this equation is equal to v epsilon theta phi sine theta d theta d phi over theta is 0 to pi and phi is 0 to 2 pi. And if we think as epsilon goes to 0, then v epsilon theta phi will just be v0. So it is a constant. So the remainder is phi is 0 to 2 pi, and integral over theta is 0 to pi, sine theta d phi, which this part is 2 pi, 4 pi. The equation is in the form of 4 pi v0. So now we multiply it by r squared, which is a surface of the uniform sphere. And this is since r squared, large r squared sine theta d phi is a little surface and sphere of radius large r, this integral is now vr dA integral over this now surface integral over the surface of uniform sphere of radius r. So we prove the mean value theorem.